Hello everyone, we continue our video series on number theory and we are going to be discussing prime numbers, fundamental theorems of arithmetic and Fermat's little theorem. So we begin with prime numbers. So what are prime numbers? A natural number p is said to be prime if p is greater than 1 and whenever p is equals to ab holds for some natural numbers a and b, we either have a equals to p, b equals to 1, or a equals to 1, b equals to p. In other words, p is prime if its only factors in the natural numbers are itself and 1. Examples of prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and so on. Composite number. An integer n greater than 1 that is not prime is called a composite number. 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20 are examples of composite number. Twin prime. A pair of prime is said to be twin prime if they differ by 2. For example, 3 and 5, 5 and 7, 11 and 13, 17 and 19. These are examples of twin prime. Perfect number. A number is said to be perfect if it is equal to the sum of all of its factors other than itself. We have 6, we have 28. They are examples of perfect number. Triangular numbers. These are numbers that can be arranged in the shape of a triangle. Examples: 1, 3, 6, 10, 15, 21, and so on. Pythagorean triples. A Pythagorean triple consists of 3 positive integers a, b, and c such that a squared plus b squared is equals to c squared. For example, 3 squared plus 4 squared is equals to 5 squared. 5 squared plus 12 squared is equals to 13 squared. So we look at some theorems on prime numbers, and the first one we look at is if p is a prime number and p divides integers a times b, then either p divides a or p divides b. So let's look at the proof. So we have p divides ab. So p divides ab if there is an integer m such that ab is equals to p times the integer m. Now we want to show that either p divides a or p divides b. So what we do is that we assume that if p does not divide a, then we show that p divides b. So suppose p does not divide a, so we must show that p divides b. So if p does not divide a, that means that p and a, they are co-prime. So if p and a are co-prime, we can find integers x and y such that px plus ay equals to 1. And we want to show that p divides b. That is, we must write b to be equals to p times an integer. So how do we do that? So the first thing we do is to multiply this particular equation by b. When we do that, we are going to get pbx plus aby equals to b, and so that means that we must be able to have p here, which is there, and also here, but we don't have p here, so we can substitute the value of ab from here. Ab is equals to pm here, so that we get pbx plus pmy equals to b, and p is common, so we have p times bx plus my equals to b. So by the definition of divisibility, p divides b. Similarly, we can show that if p does not divide b, we can assume that, okay, if p does not divide b, then p must divide a. So our next theorem is fundamental theorem of arithmetic, and the fundamental theorem of arithmetic states that every integer n greater than 1 can be expressed as a product of primes in one and only one way. So we can see if we have an integer n, so it has been expressed or it has been decomposed into product of its prime factors. So n is equals to p1 raised to power alpha 1, p2 raised to power alpha 2 times up to ps raised to power alpha x. So let's look at the proof of the fundamental theorem of arithmetic. So if n is a natural number greater than 1, then n must have a prime factor. So let's call the prime factor p1. So if p1 is a prime factor of n, so then there exists integer n1 such that n is equals to p1 times n1. Now if n1 equals to 1, that means that n is also equals to p1. But if n1 is greater than 1, then n1 will also have a prime factor. So let's call that prime factor p2. So if p2 is a prime factor of n1, then there exists integer n2 such that n1 will be equals to p2 times n2. Now if we substitute n1 equals to p2 times n2 into equation 26, we will have n is equals to p1 times p2 times n2. Again, from here, if n2 equals to 1, then n will be equals to product of two primes, that is product of p1 and p2. But if n2 is greater than 1, then n2 must also have a prime factor, say p3. And if p3 is a prime factor of n2, then there exists n3 such that n2 will also be equals to p3 times n3. So we can substitute that into this, and we are going to have n equals to p1 times p2 times p3 times n3, which is this equation. Now if you look at all this, the process must come to an end, must surely come to an end after a finite number of steps. So we must find primes p1, p2 up to pr such that n will be equals to p1 times p2 times p3 times up to pr. So now let's look at the uniqueness. Suppose n is also equals to q1 times q2 times q3 times up to qs. So that means that we must have p1, p2, p3 times up to pr to be equals to q1 times q2 times q3 times qs. That's equation 29. So suppose n equals to q1 times q2 is another representation of this equation 27. So we must have equation 29. Now from this equation 29, p1 will divide at least one of q1, q2, q3 up to qs. So let's assume that p1 divides q1, and q1 is also prime, and the only divisors of q1 are 1 and q1 itself, and p1 cannot be equals to q1, so p1 must be equals to q1. If p1 is equals to q1, now if we substitute p1 equals to q1 into this equation, they will cancel out and we'll be left with p2, p3 up to pr equals to q2, q3 up to qs. Again, p2 will divide at least one of these, so let's assume that p2 divides q2. If p2 divides q2 and q2 is prime, and the only divisors of q2 are also 1 and q2 itself, so therefore we must also have p2 to be equals to q2. So we can continue with the process, and we will see that each pi is equals to some qi. Now we show that r is equals to x. So suppose r is not equals to x, that is, for example, r is greater than x. We can also look at the case where r is less than x. So suppose r is greater than x. Now this equation 29 we have here will become p1, p2 times p3 times up to px, because r is greater than x. So we are going to have px here, and from px plus 1 up to pr. Now we are going to have this equation 29 if r is greater than s. But don't forget that we have each pi to equals to some qi. So p1 is equals to q1, p2 is equals to q2, and up to ps is equals to ps. So if you substitute that on the right hand side of this particular equation, we are going to have p1, p2 up to px plus 1 up to pr equals to p1, p2, p up to ps. So now if we cancel p1, cancel p1, p2 cancel ps, and ps, we are going to be left with px plus 1, px plus 2 up to pr equals to 1. And this is impossible because we are having product of r minus x primes, each greater than 1, now equals to 1. So it is impossible. So we must have r to be equals to s. So we must have R equals to S. So our next theorem is to look at how to find the number of divisors of a composite number. So suppose we have a composite number n written in standard form. So we want to find the number of divisors of this composite number. So don't forget, n has been expressed in standard form, that is n is equals to p1 alpha 1 times p2 alpha 2 times ps up to times ps alpha s. Now if you consider this first term, p1 raised to power alpha 1, what are the divisors of p1 raised to power alpha 1? If you look at p1 itself, the divisors of p1 are 1 and p1. So if you now say p1 raised to power alpha 1, we are going to have p1 squared, p1 raised to power 3 up to p1 raised to power alpha 1. It's just like, for example, you have 2 raised to power 5 and you are looking for those the divisors of 2 raised to power 5. For example, 1 will divide any number. 2, we also divide 2 raised to power 5, that is 2 in 2 raised to power 5, that's 2 raised to power 4. So we have 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, and 2 raised to power 5 itself. So the number of divisors of p1 raised to power alpha 1 will therefore be alpha 1 plus 1. The case of 2 raised to power 5, we see that we have 1, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, 2 raised to power 5. That's 6. So for p1 raised to power alpha 1, it will be alpha 1 plus 1. So for 2 raised to power 5, that's 5 plus 1. So similarly for p2 raised to power alpha 2, we are going to have that to be alpha 2 plus 1, and up to ps raised to power alpha x, it will be alpha x plus 1. So the total number of divisors of an integer n written in standard form as this will be alpha 1 plus 1 multiplied by alpha 2 plus 1 multiplied by up to alpha x plus 1. Now let's look at an example. Suppose we are asked to find the number of divisors of 360. So 360 can be written in standard form as 2 raised to power 3 times 3 raised to power 2 times 5 raised to power 1. Now from here we see that our p1 is 2, our alpha 1 is 3, our p2 is 3, and our alpha 2 is 2, and our p3 is 5, and our alpha 3 is 1. So the number of divisors of 360 will be alpha 1 plus 1 multiplied by alpha 2 plus 1 multiplied by alpha 3 plus 1, and if we substitute, we are going to get 24. So the total number of divisors of 360 is 24. Now we look at what we call the Euler-5 function. The Euler-5 function of a positive integer n is the number of positive integers a less than or equals to n and that are co-prime with n. For example, if you are talking about the Euler-5 function of 8, the Euler-5 function of 8 is 4, because we have 4 numbers between 1 and 8 that are co-prime with 8. And those that is, we have 1, 3, 5, and 7. They are co-primes with 8. They are integers less than 8 that are also co-prime with 8. For prime numbers, the Euler-5 function will be p minus 1. For a greater than 1, we also have the Euler-5 function of p raised to power a to be this, p raised to power a minus 1 multiplied by p minus 1. So sometimes we can multiply the Euler-5 function of two positive integers, that is phi a times b is equals to phi a times phi b, and that is when a and b are co-prime. Let's look at an example. For instance, if you want to find the Euler-5 function, excuse me, if you want to find the Euler-5 function of 12, for example. So don't forget that 12 is 4 times 3, 4 times 3. So we can see that 4 and 3, they are co-prime, and we can put that in standard form. So that means that we can use this. So we can put that in standard form, and we are going to have 5, and 4 will be 2 raised to power 2 times 5 of 3 raised to power 1. And we can see that this and this, they are prime, so we can use this formula. So for the first one, our P will be 2 and our A will be 2. So we are quickly going to have 2 raised to power 2 minus 1. That's for the 2 raised to power 2 minus 1, and this multiplied by P minus 1, that's 2 minus 1. 2 minus 1. Don't forget that is here, this one will be P, and this one will be A. And for this one will be P, and this one will be A. One will be A. One will be A. So for this one, so let's close the bracket. So now for this other one, we are going to have 3 raised to power 1 minus 1, and into bracket 3 minus 1, P minus 1. So that's 3 minus 1. So we can close. So if we solve this, 2 raised to power 2 minus 1, that's 1, and that's 2 raised to power 1, that's 2, and 2 minus 1 is 1, so this one will be 2. So we are going to have 2 times 2, and that will give us 4. So the Euler 5 function of 12 is 4. It is very easy for us to know, so but we are talking about in case of maybe we have large positive integer. So we know already that the numbers that are less than 12 and that are relative prime with 12, they are 1, 3, 5, 1, 5, 7 and 11. 1, 5, 7 and 11. So you can see that is 4. Okay, so we quickly look at Euler's theorem, and let a and n be integers such that n is greater than 0 and a and n are co-prime, then a raised to the 5 function of n is equivalent to 1 modulo n. And also we have the Fermat-Little theorem, and it says let p be any prime number, and suppose p does not divide a, then a raised to power p minus 1 is equivalent to 1 modulo p. Sometimes we can determine whether a number is composite without even finding its factors using the Fermat-Little theorem. So we look at all these and the Chinese remainders theorem, the Wilson theorems and others in our next video. Thank you very much.